All right. So related rate is when we're taking, so actually, I'll just put the first example up there because honestly, it's easier to look at an example. So this is literally what a related rate says. We're looking at how the change of one thing affects the change of another thing. So as air is being pumped into a balloon, its volume increases, which makes sense. So we know how much the volume is increasing because we know how much air is being pumped into the balloon. So we can figure that part out. What we want to know is, well, how fast is the radius of the balloon changing? So how fast is the balloon getting bigger? Okay. So to do that, we need some calculations to be able to figure those things out. All right. So what do they give me in the problem? First of all. So what information did they give me? All right, so they gave me a problem. They gave me what I'm going to look for, right? The diameter is 50 centimeters, which means my radius is what? Right, because remember it's half. So okay, so that's basically the question part of it. That's what we're going to actually use to plug in. They gave me the volume, right? But did they give me the volume, or did they give me how much the volume is changing? The volume's changing, which means that's a what? What is that unit then? It's not just a simple unit like area and things like that. It's as it's changing. So that is a slope or a rate of change, which means it's a derivative. So dV over dt is 100 centimeters per second. So that is a derivative. All right. So we've got those pieces of information. And I'm looking for how fast the radius is changing, right? So I'm looking for dr dt. That's what I'm looking for. Okay. So what do we know about the volume of a sphere? Anybody remember your geometry and remember the formula? Okay. Somebody ask Google the formula. Yeah, actually it is. Four over 3 pi r to the third. Volume is cubic, so that's why it's to the third. All right. So I got this formula. How would I get this and this? Solve for r? I could solve for r. The problem is I don't know volume. So solving for r is not going to help me find something because I don't know the volume to plug in. But that's going to give me the volume. That's not. Is that going to give me the volume, or is that going to give me the change in volume? Right, but we don't know that. We don't know. We can find that, but we have the change in volume, and I'm looking for the change in radius. So plugging in 25 for the radius would give me the volume, but that's not going to help me find the change in radius as my volume's increasing. Yeah. All right. So if I take, so I'm looking at the derivative in terms of time, right? So, okay. So let's take the derivative of this function. See if that helps. I'm going to erase and move it over. Okay. So what's the derivative of v? Remember, we're differentiating based on t, not v or r. So the bottom is going to be t. So if we're differentiating y in terms of x, remember I have to do the y prime, right? Or the dy dx. Put it there. So the same thing I got to do here. So I have dv over dt equals. Okay. What's the derivative of 4/3 pi r to the third? Yes. So remember that 3 is brought down and then that's subtracted. We're missing one thing. Remember, we're differentiating based on t, not r. So I also need the dr dt. All right. Everybody with me to that point? That's the hard part. Everything else after this point becomes easy. Everybody understand where the dv dt comes from? Everybody understand why I have dr dt? When,
say you had an equation 2b, you had 2dv.
yes. Yep. Or if you had v squared, like, yeah, you would have some other stuff there. All right. So what do we need? What was the question asking for? The chain, how fast the radius is increasing, right? So it was asking for dr dt. So I need to solve what I just did for dr dt. So if I solve, I have to then divide basically that over. So I have 1 over 4 pi r squared dv dt equals dr dt. Okay. 1 over 4 pi. What's r? 25. What's dv dt? 100. So now I can just go to Desmos and get that answer. Over 4 pi. So there's my answer. And that would be in, so the other thing that's actually really important in terms of this is the units. So it'd be that, and it'd be centimeters per second, because the radius is increasing by centimeters, and it's per second. That's related rates. So I said, we're going to talk about concrete examples on where the calculus is used, special differential calculus and implicit differentiation. And as like, we sit there and go, we have all these differentials and stuff like that. We're like, where are you actually going to use it? This is typically the types of problems where you actually would really use it. When you're looking at, we know one thing. We know how it's changing in one direction or one way. And we need to figure out, well, how is it changing in a different way? What else is changing along with that? So, like when a rocket's going up and we know that it's burning fuel at a specific rate, we can figure that part out. Well, how fast is the weight of that spaceship and that rocket actually changing? Because as the weight decreases, it needs less power to actually increase in speed. Therefore, we might not need as much fuel at the beginning to get the speeds that we want. So those are related rates. When we're looking at one thing changing, how does it impact other things that are changing that are related to it? It can't be with anything. Like you can't say, okay, the rocket, how we know how fast the fuel is going out of it, so how cold is the outside of it? Those aren't related. So that's why the related piece is actually very important. They have to be some kind of a formulaic change between those two things. And like this one, volume and radius are related to each other. So that's how we can do related rates. All right. Here's a great problem solving strategy. This is basically how you're going to do these problems. Read the problem. And then reread the problem. Any type of word problem in math, read the entire problem before you start doing it. Then go back and start pulling information out of it. Do not start pulling information out of the problem before you read it. Because sometimes there's information that you don't need in the problem. That is extremely possible, especially in problems that you deal with in real life. You might have a ton of information you don't necessarily need to solve the actual problem. Also, you might be using it in different ways than you originally thought until you get to the end. Draw pictures. Pictures are always nice. Sometimes pictures are better than others. Like I don't think we needed a picture to visualize a balloon blowing up. I think we can all visualize that fine, so we don't necessarily need that picture. But some of the other ones we're going to look at, definitely having a picture is going to be helpful. Then we talked about, then I did introduce notation. We did the dV over dt. So by doing it in a specific way, using the differentials, we then use that to say, okay, how do I actually need to solve it later on? So the notation is actually very important. Whenever you have something that is changing over time or a rate of change or a slope, that's a derivative. So write it like that. And actually, the terms that they gave me, if you look at the original problem, dictated how I wrote it. So you'll see it was volume increases at a rate of 100 centimeters cubed per second. Centimeters cubed, that's volume. Second, that's time. That's where that dV over dt came from. Okay, you had that term. The last one, how does the radius change over time? So it's dr over dt. Okay, it's centimeters over seconds. So you can use that just like you did in algebra when you're talking about rise over run. You wrote the units in that way. Rise over run is no different than a derivative. Those are the same exact things. So we're going to use them the same way. Express the given information and required rates in terms of derivatives, as we just talked about. Write an equation that relates the two quantities or the quantities that we're looking at together. That was that volume equation. We can figure out the volume of a sphere that is related to the radius. So we had that equation, we were able to break it up. We will see example 3 in a few minutes. So, chain rule. When we were doing the derivative of this, that's the chain rule. Okay, it was also implicit differentiation when we were doing it. That's why we had the dRdt there. Then substitute back in and solve what we're missing. So, all right. The fear of every person who ever works on a ladder. How fast are you falling to the ground? All right. Read the problem. This is one that drawing a picture is kind of nice and not too hard. So that's what we have. Now we're looking at, so the change over here, that would be dy over dt. The change over here, going this direction, would be dx over dt. The change on the wall, is that going to be a positive dy over dt or a negative dy over dt? It's going to be negative because it's going down. Understanding that's going to help you because when we get the answer, it should come up with that. Okay, we should see that negative change. And then dx dt is going to be positive because it's going away from the origin. All right, so what do we know? What did they give me? So they gave me dx over dt is 4 feet per second. And we want to know the dy over dt, right? At x equals 6 feet. Yeah. Yeah, velocity, because that's what we were talking about last class. We're looking at the velocity is the derivative of the position. The derivative of velocity. Yeah. Yep. The nice thing is, and this is one of those things that you normally don't think of because we just do it so often. Like miles per hour, by definition, is a derivative. You deal with it every single day. It is the change in miles over the change in hours. That is by definition a rate of change, so it is a derivative. You would never think about that in terms of a calculus problem, but that's what it is. So anything that has that fractional unit is in essence a rate of change. Therefore, it is a derivative. So, and when you get the like second squared or things like that in the bottom, when you get acceleration stuff, that ends up being a second derivative because now the bottom is squared part of it. So that's where those things come from. All right, so we need an equation to model this. So what is my equation going to be that's going to relate the x to the y? Because unlike the last one, this one's not a nice little volume formula or area formula. So what would be the formula that we're going to use for this one? Yeah, we're going to use the Pythagorean theorem. So I have x squared plus y squared equals 10 squared, or 100. I'm going to change it to 100 just because I don't feel like rewriting it again for the 100. All right. We've got our formula that relates them. What's the next step? So if we go back and look at our steps, we've now read the problem, we've drawn a diagram, we've introduced notation, we've expressed it in terms of related rates, we wrote an equation for it. We're on step 6. Chain rule. Find the derivative of that. All right, so what's the derivative? The key thing that you do not want to forget when you're doing this is those. Okay, don't forget those. And the reason we need them is because we're doing the derivative based on t, not x or y. Because when we did implicit differentiation, remember we were doing it based on x. So the x didn't have a derivative next to it, only the y did. But in these, we're doing the derivative based on t, so we need them both, because technically the t isn't even in the problem. But x is a function in terms of time, and y is a function in terms of time. All right, so you can do this a couple different ways. Like you can solve this right now for dy dt and do it that way. Honestly, I would just plug in right now, and then we'll solve the problem. So what do we know? So we know dx dt is 4 feet. Okay, so we know that. And we know x, right? X is 6. So we know x is 6. And we know dy dt is, or dx dt is 4. Do we know what y is? Okay, can we find it? How? Yep, plug 6 into the Pythagorean theorem. So 6 squared plus y squared equals 100. Or Actually, this is going to actually be easier looking at that way. 3, 5. So this would be a what? What's the special Pythagorean theorem? The one that always is seen? 3 what? 5. 3, 4, 5. So this is going to be 8. But I will do it out so you can actually see it. Three, 4, 5, and 5, 12, 13. Those are the two Pythagorean theorems that will come up a lot when you're doing your problems. And then any multiple of those. So in this case, 3, 4, 5, but it's the multiple of 2, 6, 8, 10. It could be a multiple of 3, 3, 12, 15. It could be any of those multiples. The other one is 5, 12, 13. Those are the other Pythagorean triple that will show up a lot. So I know y is 8. And we don't know dy dt. Okay. So 2 times 6 times 4, 48 plus 16 dy dt. So dy dt equals negative 48 over 16, which is negative 3. Feet per second. So you're falling to the ground at a rate of 3 feet per second. Yeah.
Was it asking us how fast it's falling? Do we specify negative 3 feet per second? Just say 3 feet per second. Can you put down our final answer?
Yes. And well, depending on how you write the answer, if you write he's falling at 3 feet per second, that'd be fine. I can almost guarantee you Alice is going to want it as a negative, so make sure you put the negative sign. So that was why at the very beginning we were looking at it, it's like, okay, that dy dt should be negative. That's also a way we can look at the final answer and go, okay, I've got this answer right. I got a negative value. That makes sense. So I would leave the negative sign there. But again, like saying the word falling technically meets that if you write it out as a sentence. But the negative side means now you don't have to write that falling word out. So let's see. That means you're going to hit the ground in just over 2 seconds. All right. Next. All right. Draw a picture of this. I want to see what your pictures look like. Because sometimes drawing the picture can make or break these problems. If you can't visualize what the problem is when you're looking at how to relate things, you might not be able to figure out how to do it. So sometimes with pictures, draw me a picture. So it tests all your drawing skills. The engineers are in the class. I'm not expecting artistic masterpieces. All right. Now I cheat. I already have the picture. All right. So when you're looking at this, some of the information that's actually really important is, first of all, making sure it's a cone. Second of all, is understanding where the water is in the cone. Okay, and how that water is changing. So in this case, if water is being pumped into the tank, what do you think the radius is going to do as the water is being pumped into the tank? It's going to be increasing. And understanding that dynamic is going to help you in the problem. Just like with the ladder, we know it was going to fall. We knew it was going to be negative. Like that information is important to make sure that when you get your answer, it makes sense. Okay. All right, so we've got this. So we've read the problem, we've drawn the diagram. Now let's introduce some notation. So what information did they give us? So they said the whole thing is 4 meters tall. So we've got that. And we know that the radius of the cone appears 2. So we've got that. That's on my picture. Yep. So we have the dV dt is 2 meters cubed per minute. And what else do we have? So the height is 3 meters. Okay, and what am I looking for? The derivative of height. We're looking for dH dt. We're not looking for how fast the radius is changing. We're looking for how deep the water is. So, or how much the water level is rising, which would be the height. Okay. All right. So what's the formula I'm going to need to relate these? So we're trying to relate volume to height. So what's the formula that's going to relate volume to height?
Do you need the volume of a cone?
Hold on, I didn't hear you. What'd you say?
Do you need the volume of a cone?
Volume of a cone, yes.
Okay, so it's pi r squared h over 3.
Yep. Thank you. So that's the volume of a inverted or a circular cone. Any formulas I'll give you. Actually, the one that's going to be on the test will not be a volume one. So you will not need to know a specific volume formula. One will be a Pythagorean, and there's going to be a trig one we're going to do. Huh? In fact, you're going to need a formula to be given it. I'm not going to give you one that's going to need a volume formula. It'll be a Pythagorean theorem problem, and then there'll be a trig problem one, where you need like sine or cosine or something. Possibly, and I would give you the formula. Yeah, I would. I'm not testing you on your knowledge of formulas, so I would give that to you. So. All right. Anybody see a problem? And everybody's brain's going, okay, he asked if I saw a problem. There has to be a problem. Yes, there's a problem. What is the problem? Yeah, we know nothing about radius in this problem. So how can I change and be able to relate the height, figure out R in terms of height, so I can get rid of my radius? So again, this goes back to your geometry lessons. We have a triangle here. And we have a triangle there. Those are similar triangles. Means, because all the angles are the same. So, which means I can relate them to each other using similar triangles. So, in this respect, R over H equals 2 over 4. They're related to each other. Down a little bit. Okay, so R over H equals 2 over 4, so that means R equals H over 2. So I can rewrite this problem here now in terms. I'm going to pull the 1/3 out so I don't have to deal with that part. Of just height. Can I clean that up to make my life easier? So we can square the fraction, get rid of the parentheses, and put things together. So I have 2 squared is 4, so I have 1/12. Actually, I want to put the pi on top of that. And then I have h to the 3rd. That's h squared over 4. That's where the 12 came from, and the other 2 for the h. All right, so All right, so we have that volume now. Now what do I do? Take my derivative of it. Pi over 4 h squared dh dt. All right, let's plug in everything we know. So 2 equals pi over 4 times 9. So I have 9 pi over 4. So I have 8 pi over 9 equals dh dt. Oh, not 8 pi. 8 pi. Pi's on the bottom. 8 over 9 pi. And that would be in meters per minute. If anybody's wondering the actual decimal, it is 0.28 meters per minute. All right. That makes sense? Okay. All right. Draw me a picture for this one and fill out all the information you can. I'm actually going to change the problem a little bit. So here is car A and car B. Right? They want to know how fast they're approaching each other. So if two cars are coming head on to each other, that's easy, right? You just add. If they're behind each other, you would subtract their speeds, and that's how fast they'd be approaching. However, they're approaching an intersection. The distance that they're approaching is actually that hypotenuse line. We want to basically find out how fast that hypotenuse line is shrinking, because that's how fast they're approaching each other. So now let's think about this problem. Why is this problem actually something that would be realistic? You're coming up to an intersection, you have a green light, you're going 50 miles an hour, so you're going to keep going, right? Because you have a green light. However, you look to your left and realize the other car is flying and is not going to stop. No, you're going to hit your brakes. But who is going to take out their notebook after the accident? The insurance guys, the police, and everything else to figure out when that light changed, who was at fault. Because if that light changed while you were going under it and it was green for the other guy, okay, it's like that light might have turned red before you got under it because it's like, oh, I'm going to beat the yellow light because we all know I'll do it. It's like, so the crash investigator is going to have to try to put that back together. And I will tell you, when those two cars hit at that speed, that you're going to find out the speed in a minute, they're not going to sit there and stop. They're going to be flung. So when you get to that accident scene, you're not going to be in the middle of the intersection. So they're going to have to try to recreate what happened in that intersection. Okay? So let's find out how fast they were when they were 500 feet apart. Not even when they intersected. We're going to figure it out 500 feet apart because that's about 0.1 miles. I decided I didn't want to do 0.01 at 50 feet. I figured we'll do 0.1. Okay? Well, no, we're going to do miles. Yeah, that's why I did 0.1 instead of going down even further. So, and I didn't want us to have to do the conversions from miles per hour to feet per hour and stuff like that. All right. So what's the formula that I'm going to use to relate these? Or actually, before we do that, what information do I have? Let's do that part. Because we have a lot more information in this problem. What information do I have? How fast is car A going? 50 miles per hour. So that would be, I think they made X, so that's X. So dx dt is 50 miles per hour. And then d, or dy dt, is 60 miles per hour. We know x is 0.1. We know y is 0.1. And I want to know what? What do I actually want to know? We want to know how fast that's changing, because that's how fast they're getting closer together. So we want dz dt. All right. So what's the formula I'm going to use? Yep. Yep. So x squared plus y squared equals z squared. So we're also probably going to have to figure out what z is, right? So if we plug in 0.1 squared plus 0.1 squared, and then we take the square root of that. We get 0.141. So that's the z. If you did 0.14, that'd have been fine because it's one place more than they gave you in the problem. So as long as you're one place more than they give you, you're fine. All right. So what do I got to do next? Take my derivatives. So I get 2x dx dt plus 2i dx or dy dt equals 2z dz dt. So 2 times 0.1 times 50 plus 2 times 0.1 times 60 equals 2 times 0.141 dz dt. So you're going to impact at 78 miles an hour. That's an yes. Yes, they would actually in this situation. Very good. This is what happens when I change numbers in a problem and don't think realistically. Yes, they probably would end up missing each other because one's going faster than the other one. The original problem was 0.3 and 0.4, and I just didn't want another 3, 4, 5 triangle. However, the funny part about it, the actual speed comes out to be exactly the same. So if one car is going 50 miles an hour, one car is going 60 miles an hour, and they impact like you hit a wall at 78 miles an hour. Okay. Not going to be fun to walk away from. Could. Hitting a wall at 78 miles an hour absolutely could kill you. That's the speed of the impact. So what's this? What's the police officer and investigator would say? Slow down. Especially when you're coming up to an intersection. You have no idea what everybody else is doing around you. So, or worst case, don't speed up. That'd be the worst thing you could do. Okay. So yes, you're not going to apply to your little notebook, but somebody is going to. And they also have to figure out how fast you were going. So, all right. Last one of the day. All right, draw me a picture. My picture is going to be prettier. The book actually has a really cool picture for this one. It's not just a triangle. Now the book's just showing off. As long as you had the triangle on the bottom, you were good. So up till now, we've done pretty much like Pythagorean theorem problems, a couple volume problems. This problem is a trig problem. Because we're going to be looking for the angle that the spotlight is rotating. All right, so we have our cool picture. Still a right triangle. So we're going to use right triangle trig, which would be nice. All right, what information did they give us? Yeah, so that's dx dt. So dx dt is going to be 4 feet per second. They gave us the adjacent, actually. The adjacent side is 20. They gave us the opposite sides. Oh, well, yeah, they gave it to us there. Yeah. So they did tell us x is 15. Which is the opposite. Anytime you're looking for an angle in a triangle, think back to trig with your opposite, adjacent, hypotenuse pieces. Huh?
What is after X?
Opposite. Opposite, adjacent, hypotenuse. SOHCAHTOA. All right. So how am I relating these things together? Okay, opposite and adjacent is going to be tangent. So SOHCAHTOA, TOA. All right, so the tangent of theta equals x over 20. Huh? It would, but remember, we're looking for the change. We're going to use the 15 to figure out, like, that's where we're going to plug in at the end to figure out, like, what the change is at that point. But I want the change in that theta. So that's the piece that we're looking for. We're looking for d theta dt. So yes, I can figure out the angle at that point, but I want to know the change in the angle. So in essence, how fast do I need to have the spotlight turning to keep up with the person? All right, so what would you like to do with this problem as it's written? Okay. So what is the derivative of tangent of x or tangent of theta? So I will tell you on your test, the three you will need to know: sine, cosine, and tangent. So secant squared theta, d theta, dt. Don't forget that. Equals what? Nope, you're doing it over t. So it ends up being 1 over 20 dx dt. The one nice thing about related rates is they're almost always based on time. So you'll almost always do your derivatives based on t. We're looking for d theta dt, right? So let's clean this one up again. We haven't done that in the other problems, but I think this one's going to be a little nicer if we clean this up a little bit. So I have 1 over 20 secant squared theta dx dt. If secant squared theta is on the bottom, what would it be on the top? What's the reciprocal of secant? Not cosecant, cosine. All right, so I know the x dt is 4. But I need to know what cosine squared theta is. I know that this is 15, right? They told me that x is 15. So for cosine, what two sides do I need? Cosine is adjacent over the hypotenuse. So
Instead of doing that. Like it. On the. Not the range. Less steps, right?
I don't know if it's going to be any really less.
Otherwise, we have to find.
You have to find the hypotenuse,
hypotenuse and
but you're just going to use the Pythagorean theorem for that.
Oh, wait, yeah, no, it wouldn't be, sorry.
Yeah, I'm thinking it might not be less steps. I think it'd be easier to remember. So to find cosine of theta, I need adjacent over hypotenuse. So I need my hypotenuse. I know my adjacent is 20. I need my hypotenuse. So I'm just going to do the Pythagorean theorem. So it's the square root of 15 squared plus 20 squared, which equals 25. Because again, it's another 3, 4, 5 triangle. So that's 25. And then that's squared, right? So 20 over 25. Squared. So now we can just plug all that in and find the answer. And we get 0.128. And it's radians per second. Okay. Hey, Brad, before you run away, can you check and make sure my desks are fine? Can you check and make sure my desks are fine? Yeah. 21. I got 21. I got 16, 3, and then the 2 on the back wall. Okay, that's fine. All right, so we got 0.128 radians per second. That would be, yeah, pretty much for these. It could be degrees. And they would ask that in the way, but to do that, you'd basically have to find the radians and then convert it to degrees. You're not going to find the degrees just by doing the calculation. So unless they give you that information, like you're always going to find it in terms of radians. Now, if you had done yours the way you were thinking about doing it with the arc tangent, you could have technically found it in degrees at that point, but because you would have done degrees in your calculator, it would have given to you in terms of degrees instead of radians. So, but you still would have had to plug it back into the rest of that formula. But for this case, just keep them as radians. All right, I'm going to show you what the ALEKS problem looks like. This is literally what the ALEKS problem looks like. It's finding you have to basically do exactly what we just did there. You're going to put the actual answer in here, and then you're going to tell if it's increasing, decreasing, or constant. If it's increasing, that number, it's positive. If it's decreasing, it's negative, and it's constant. It would have been 0. Yeah, this one's you're going to do exactly the same way that we just did. The one we just did. Oh, they're moving, right? So this one I think is Pythagorean theorem. This one might be a Pythagorean theorem problem.
Well, I think,
ALEKS only has 2.
but you could solve it without the. By just using similar triangles. It's
Maybe.
kinda how Alex showed it.
Oh, maybe, yeah. I was like, the nice thing, so in Alex, there's only two types. It's either the triangle ones or the trig ones. Those are the only two types of problems you're going to see on the Alex one for this section. All right, y'all ready for your test next week?
Test is on Thursday.
Test is on Thursday. Chapter 3 is done and closes at midnight on Thursday. And then it kicks you over to chapter 4. So I will set it so that everything opens up after Thanksgiving. So after Thanksgiving, everything will open up. So you can go back and fill in other modules and chapters if you didn't finish the chapter.
There's one more module after this. Other work topic one. It's the one with like more trigonometric.
Yeah, that's what I said. There's a trig problem. But it looks the same. It's just set up with the trig problems. It's the only two. What?
Let's try it before this class, but I was having trouble understanding.
Send me a picture of it. I can walk through it. Yep. Yes, class is over.